Hello all, welcome to the lecture series on analog communications. In this module, we discuss about the manner in which we can easily estimate the figure of it in continuous wave modulation schemes. In the previous lectures, we have studied enough about what is modulation, what are different types of modulation techniques, an elaborate classification of modulation techniques as continuous wave modulation and pulse modulation. Within continuous wave modulation, we have talked about amplitude modulation, frequency modulation. Further, amplitude modulation we have also classified into a broad category: double sideband full carrier AM, double sideband suppressor carrier AM, single sideband suppressor carrier AM, as well as vestigial sideband suppressor carrier amplitude modulation techniques. We have seen how these schemes are better over the another in terms of bandwidth conservation as well as power conservation also. However, there is a small question arises. When so many continuous wave modulation techniques are existing, which scheme is better? That is the question to be answered. Earlier we mentioned that among AM and FM is better. That is, the frequency modulation is better in terms of noise performance. It is a qualitative parameter to say FM is better. But this module concentrates on deriving it quantitatively. We are going to obtain one mathematical expression which is going to indicate that frequency modulation is far better than amplitude modulation techniques in terms of noise performance also. When that question arises, or when it is thought of obtaining the quantitative parameter, the immediate parameter that can be thought is the figure of merit. Figure of merit is mostly used in communication systems, or particularly analog communication systems, to identify which modulation scheme is better than the another. If I define figure of merit, it is given as figure of merit F equals to gamma equal to signal to noise ratio at the output divided by signal to noise ratio at the channel output. The numerator corresponds to whatever you measure at the receiver output. The denominator corresponds to whatever measured at the receiver input, which is nothing but the channel output. This is because the channel output is given as input to the receiver. That is why the numerator signal to noise ratio SNR of O, the denominator SNR of C. C corresponds to output of the channel. Then what is SNR? Signal to noise ratio generally is defined as the ratio of average signal power to average noise power. In this context, if you want to estimate the signal to noise ratio at the receiver output, it is defined as average signal power at the receiver output to average noise power at the receiver input. Subsequently, SNR of C, that is signal to noise ratio of the channel, can be defined as average signal power at the channel output divided by average noise power at the channel input. These are the fundamental definitions we must remember before proceeding into how can we estimate the figure of merit from the knowledge of signal to noise ratio. From these two expressions, that is SNR of O, SNR of C, it is clearly known that we have to estimate the average power. It can be signal power or noise power. So before we go for that one, we must know what is the expression for average power of any signal. The average power of any signal can be obtained from the time domain by using the expression 1 over t integral 0 to t x square of t dt. This is the standard expression which we have learned from our fundamentals of signals and systems. T is a time period. and it cannot be called as a mean square value. Average power is the mean square value. X of t is the time domain representation of the given signal for which you want to estimate the power. However, there is one constraint on this. If you know the mathematical expression, we estimate the power from this expression. In the non-availability of the mathematical expression, how can we go ahead? Means there is another manner where in which we can also obtain the average power of a signal. That is, have a glance, average power can also be represented as integral minus infinity to infinity s x of f df. What is this fx of f? Sxx of f is the power spectral density of given signal x. The meaning of this mathematical expression is average power in frequency domain is nothing but the area under the power spectral density curve. Thereby which we can see there are two types of two ways to calculate the average power. One in time domain, the another in the frequency domain. If mathematical expression available, go for time domain representation. In the absence of the mathematical expression, we can directly go for frequency domain from the knowledge of power spectral density. In which cases the situation generally arises is say case of noise. Noise generally has no mathematical expression because noise is random. We have defined earlier, noise is defined as the unwanted form of energy that is going to interfere with proper transmission and reception of the signal. And noise has no mathematical expression because it is random in nature. So how to estimate then? Assume some noise. Generally, we assume the noise as a white noise whose power spectral density is given as S W of F equal to N naught by 2 for minus infinity less than F less than infinity. This is the standard assumption generally made. We assume the noise as white noise. Why we assume white noise? Because as the white color contains all the colors, this noise is assumed to be present for all frequencies. It indicates that it is the worst ever assumption we made, noise at every frequency component. By making this assumption, we are evaluating the performance. So as noise is not defined in time domain, we assume the noise as a white noise and mention its power spectral density in frequency domain. Once power spectral density is available, directly area under the power spectral density curve is nothing but the average power. Hope now it is clear. So in time domain, we estimate the average power for the known signals. In frequency domain, we obtain the average power of the unknown signals, which cannot be represented mathematically. With these two notations available for estimating the average power, let us slowly go into the fundamental steps in estimating the figure of merit. The first step in the estimation of figure of merit will be draw the receiver model. This is a very important step in the process of obtaining the figure of merit. Why? Because whatever blocks present in the AM receiver or FM receiver, all of them are not going to contribute for the final figure of merit estimation. We all know that the front end of the receiver is RF amplifier, which is a wideband amplifier, that is followed by IF amplifier, which is a narrowband amplifier. So whatever you are going to measure at the receiver output, it is not depending on the RF amplifier, but depending on the IF amplifier. What the IF amplifier will do? The IF amplifier is not going to pass all the signals whatever received. It is going to restrict the signal up to specific band, having center frequency at IF and pass to the demodulator. So the generalized diagram for the receiver model can be represented in this manner. The input to the receiver always is the modulated signal S of t. which is corrected with the white noise W of t, followed by an equivalent IF filter. Why we use the word IF filter here? Because this section, that is IF amplifier, is going to convert the wideband signal into narrowband signal, which is followed by the demodulator. This is the standard receiver model we consider, and output is the demodulated signal. Okay, so if I call this as x of t, for example, I denote this as y of t, demodulated signal. Now, which demodulator you are using depends on the which modulation scheme. Suppose the modulation scheme is double sideband full carrier AM, I will use envelope detection. The modulation scheme is double sideband suppressor carrier AM, I use coherent detection. If the modulation scheme is single sideband suppressor carrier AM, again I use coherent detection. And for FM, we will use a limiter followed by a discriminator and the low pass filter. So the first step in the process of evaluating the figure of merit is drawing the receiver model. And then this will be followed by estimation of, second step will be estimation of input signal power SI. I denote it as SI. Estimation of SI. What is SI? SI corresponds to input signal power. How we estimate? What you are estimating? Signal power? No. What is the input signal? Modulated signal. For example, say, for example, for DSB SC AM, input signal, that is a modulated signal, is AC cos omega CT into M of t. So this is the input signal. Then how to get the power? So input power, I just take it as a SI. Input signal power SI equals to 1 over 2 pi 0 to 2 pi S square of t dt. If it is full carrier AM, S of t will be AC cos omega CT into 1 plus Ka M of t. So based on the input modulated signal, input signal power will vary. This is the first step in the estimation of figure of merit. Then step number 3. What we are going to calculate in this step is Ni. Estimate Ni, which is nothing but input noise power. Ni. How we estimate? As already mentioned, we don't know the mathematical expression for noise. So what we are doing and what we are proceeding, we are assuming that input noise is SW of F equal to N0 by 2 minus infinity to less than F less than, and we have to get the average noise power using this expression minus W to W N0 by 2 df. N0 by 2 is a constant. So how it will be? N0 by 2 integral minus W to W 1 df. So integration of 1 is F now. Integration of 1 will be okay. So input noise power will be equals to N0 by 2 into W minus W, which is nothing but W N0. This is the input noise power. However, one doubt comes. In the earlier definition, we have mentioned that noise power or power in frequency domain should be evaluated between minus infinity to infinity. Then why minus W plus W is taken? Because the input noise power at the channel output is calculated in the message bandwidth only. One point remember forever. The another point is this step, that is estimation of input noise power, is common to all modulation schemes. It can be double sideband full carrier AM or SSB or FM. This step is common for all. So what you have got till now, we have estimated the input signal power, we have estimated the input noise power also. Then what is the next step? Calculate or estimate SO, that is output noise power. Excuse me, it is not the output noise power. We have to estimate the output signal power. But this step, as well as estimation of output noise power steps, will be a little typical. Why? Because the output of the IF section or IF filter, which is going to be a band limited one, is to be passed through a demodulator. So the demodulator output contains the signal and the noise components. And we have to estimate the corresponding signal power from the signal component and noise power from the noise component by using standard expression. We have the expression for the signal at the output. So SO will be using this expression here. Okay, SO equal to 1 by 2 pi, 0 to 2 pi. I call, for example, YO of t dt square, where YO of t corresponds to the signal component present in the output signal Y or Y of t. Okay, then the last step in this evaluation process will be estimation of output noise power. Estimate NO, that is output noise power. And what noise is coming actually at the output? At the output, we are getting the narrowband noise. Why? Because input noise is W of t. It is a wideband noise. It is passed through equivalent IF filter, which is going to generate a narrowband noise N of t, we call generally. This is represented as NC of t cos 2 pi FCT minus NS of t sin 2 pi FCT. In this estimation of output noise power, the characteristics of the IF section are going to play very important role. Generally, for double sideband full carrier AM, single side double sideband suppressor carrier AM and FM, the transfer characteristic of the IF section will be in this manner, that is FC, and this will be FC plus BT by 2, FC minus BT by 2. And what is that? This value will be nearly 1. And same is the replica at the negative frequency side also. Minus FC plus BT by 2 minus FC minus BT by 2. This IF section characteristics are going to rely on what is the center frequency of the IF section. For double sideband full carrier AM, for double sideband suppressor carrier AM, and for FM, the center frequency is FC only. Why? Because here we are transmitting both upper sideband and lower sideband. However, when we talk about the SSB, the center frequency will definitely vary based on which sideband you are transmitting. Correspondingly, the center frequency will vary. Suppose I am transmitting only lower sideband, say, so FC minus W, and this one is FC minus W by 2. This will be the center frequency of the IF section for SSB only. Similarly, negative side also, minus FC plus W by 2 minus FC plus W minus FC minus W. Sorry, this will be only minus FC. So in this manner, the characteristics of the IF section The transfer characteristics of IF section depend on out of narrowband noise which component is coming out, and thereby which we can estimate the figure of merit at the receiver output. And once they were derived, we can directly calculate figure of merit as F equal to gamma equal to signal to noise ratio at the output divided by signal to noise ratio at the receiver input, which is nothing but the channel output. Once these fundamental discussions were made, we can be able to easily calculate the gamma value. In the next lecture, we are going to discuss about figure of merit calculations for double sideband suppressor carrier amplitude modulation techniques. Thank you.